We introduced Depth Light Field Training, or DeLFT, a deep residual network that generates depth maps based on existing NeRF models. DeLFT evaluates 100 times faster than the standard NeRF network and produces consistent depth information to be used for rasterized hard shadows. Neural radiance fields are state-of-the-art novel view synthesis methods that use a neural network to estimate volumetric scene functions. To render a NeRF, techniques from volumetric rendering are used. Each ray from the viewport is sampled a number of times, the network is evaluated for each sample, and the outputs are alpha composed to arrive at a final pixel color. For the standard NeRF model, rendering one frame takes around 20 seconds on a GTX 1070 system. In some steps of the classical rasterization pipeline, the full object details are not needed. As an example, take shadow mapping. In shadow mapping, the scene is rendered from the perspective of the light source and a depth buffer is saved. Afterwards, the depth information is used to calculate occlusions when rendering from the position of the camera. NeRFs are able to generate depth maps by outputting the expected ray termination depth for each ray. However, the full volumetric rendering pipeline is still necessary. Our goal is to speed up the depth data acquisition process so render times are not effectively doubled. Neural light fields are closely related to neural radiance fields, but instead of evaluating the network for each ray sample, the output color is directly estimated through one network forward per ray. Our solution proposes a 128 node wide and 44 layer deep residual NeLF network that uses an existing NeRF to generate its training data. In order to achieve full viewpoint freedom, we employ ray reprojection onto the scene bounding sphere. The network learns a number of rays within the bounding sphere. If a viewpoint position is outside of the bounding sphere, the intersections between the rays and the sphere are calculated and the ray origins are relocated on the surface of the sphere. These are visual comparisons between depth outputs of the DeLFT model and their NeRF teacher model. A few observations can be made. The NeRF model offers higher depth resolution around small details, but the DeLFT model approximates silhouette edges better. Also, NeRF depth outputs are prone to be noisy, which greatly disturbs the shadow generation. The DeLFT model essentially eliminates the noise. To showcase the use of our generated shadow maps, a simple Pygame demo is also available. In this rendered video, we can see that using our depth maps, we achieve great occlusion effects. Here, a cube object is used in place of the Lego object to achieve a better frame rate.